Modern electronics design today almost always begins with simulation. If we go back a few decades, engineers designed circuits using hand calculations on paper, carefully verifying every step. Today, however, technology gives us a huge advantage. We can design faster, more reliably, and in most cases, with far higher quality than would ever be possible using manual calculations alone. The reason is simple. Humans make mistakes. We simply cannot compete with the speed and precision of a computer when it comes to solving complex systems of equations. In the traditional approach, every assumption and every result must be checked manually, which consumes a significant amount of time and resources. Modern simulators, on the other hand, can automatically solve extremely complex problems. Problems that would be difficult or even impossible for a human to handle within a reasonable time frame. If we look at the current state of technology, especially in areas like integrated circuit design and semiconductor physics, the level of complexity is enormous. We are dealing with models that include hundreds of parameters, sometimes over 200 or even 300 interdependent variables, just to describe the behavior of a single device. Solving such systems manually in an efficient way is simply not realistic for any engineer. That said, using a simulator is not a shortcut to innovation. Downloading a free tool does not automatically mean you can design the next breakthrough product. Without a solid understanding of the fundamentals, simulation results can be misleading, and errors can appear very quickly. This leads to a fundamental question. How does MOSFET simulation actually work? How accurately do these models reflect physical reality? And why do we sometimes see differences between datasheet values and simulation models? In this video, we will explore exactly these questions. We will connect the parameters used in simulation models with the classical equations found in electronics textbooks. The goal is not just to learn how to use a simulator, but to truly understand what happens behind the scenes, so you can better understand electronics, diagnose why circuits fail, and know how to fix them. Here we have the model for the IRF640 transistor. As you can see, it consists of a list of parameters along with their corresponding values. This is a relatively simple model. As mentioned earlier, there are models with significantly more parameters, but for a solid understanding, this level of complexity is more than sufficient. Semiconductor devices are typically presented as a group because they share a common specification methodology. Unlike simpler elements, semiconductor devices are defined by complex nonlinear equations characterized by a large number of parameters. These parameters are specified in a model statement. The general format for defining a semiconductor device in SPICE is like this. The device name, dev name, starts with a specific letter that identifies the type of component. Mod name refers to a model definition that contains all the physical and electrical parameters. Multiple devices can reference the same model, which reflects the fact that they may be manufactured using the same process. Finally, each semiconductor device definition is accompanied by a corresponding model statement, which contains the detailed parameter set describing the device behavior. VTO is the gate source voltage at which the inversion channel forms and drain current starts. Kp is the transconductance parameter. Lambda, channel length modulation. Then we have the trace resistances, Rs, Rd, Rg, and Rb. These parasitic series resistances between the external terminals and the internal nodes. Then we have the VDMOS specific parameters. Rhonex is the channel conductivity multiplier in linear region. Adjusts the channel conductance when the transistor is fully on, not present in standard SPICE. Eta is the controls the gradual transition of drain current below threshold. Then we have body diode parameters. Is the reverse saturation current and the emission coefficient. The body diode, bulk drain junction, conducts when VDS less than 0. Then we have Eg, the band gap energy. Xti is the saturation current temperature exponent. Temperature dependence of the body diode saturation current. Then we have the capacitance parameters. Cgs is the gate source capacitance. Cgdmin is the minimum gate drain capacitance. Cgdmax is the maximum gate drain capacitance. The Miller capacitance varies with VDS, small at high VDS, off, large at low VDS, on. Here we have TT2, that is the transit time. Transit time of the body diode determines the diffusion capacitance when forward biased. Then we have the temperature parameter like TRB1, bulk resistance, first order temperature coefficient. Now we could continue with other types of models that have many more parameters, but it wouldn't really make much sense here. I've displayed some formulas on the screen, so you can see that these are not just arbitrary or made-up values. Of course, there are also many models that are not necessarily accurate, but that's a different topic. In the next video, we continue.